Okay. It's the start of the class, a decent number of people are here. I guess I can get started with announcements. Oh, that clock is off. 2 minutes fast. So. We're coming up on the first test and the first set of due dates. So the first group of worksheets for chapter 2 and 5 through 7 are due on the 11th. Homework number 1 is due also on the 11th. You can turn it in as by uploading a file on Brightspace or by turning it in on paper in class if you want to do that. I'm okay with either option. So the first test on chapters 1 and 2 and 5 through 7. That first test will be on the 11th. That's next week, Thursday. I'll try to do most of chapter 7 today, and we'll finish chapter 7 on Tuesday next week, and then we'll have the test. The test is 60 to 70 multiple choice questions. I'm trimming it down from my older tests. It was a little long. There were issues with it the previous times I got the stuff, so I'm shortening. The test I had was 75, making it less questions. It's multiple choice. We're going to be using a Scantron sheet. And you get one sheet of notes to use as reference that you can bring to the test. So that's one regular letter size piece of paper. You can use both sides if you want. And lastly, please sign in on the sign-in sheet. That was all I wanted to cover. Any questions about this? I don't know exactly. Yeah.
Oh, wait, no, right, it's right again. That's 60 to 7 minutes. I'm not gonna think this.
It's 60 to 70 questions.
Yeah,
It'll be the entire class period.
gotcha.
Okay. All we're gonna be doing that day is taking the test.
Gotcha.
So it will be 80 minutes.
All right.
Yeah. But it's 60 to 70 questions because I currently have a 75 question test that I need to shorten, and I'm not sure exactly how many I'll manage to remove from it. I haven't fully gone through it yet. Okay. So, first I have a few links for additional resources. I'm pretty sure these are the ones that are up in the slides that are on Brightspace. I'll try and remember to update those slides, or it should be, I'll just chat after class. But these are a couple of links. Welsh Labs has a couple of interesting videos on YouTube about how Kepler discovered his laws, the whole process he went through to figure out actually that those orbits were elliptical, and how he got that information from the data he had, which was actually really quite interesting and clever. And then Crash Course has a podcast called The Universe on the history of the universe and the future of the universe. So, it covers the history of the universe, and then it covers the possible ways the universe could end. And that's presented by John Green and Dr. Katie Mack. And that's also available on YouTube. There's a link to the playlist there, but it's also a podcast. So if you listen to podcasts, you can download it in your podcast app of choice. So, we're starting chapter 7. This is an overview of the solar system. We're going to go over, sort of take a tour of the solar system, go over the various things that are in the solar system, and talk about it as a whole. And then in later chapters, we'll handle each of these bits in more detail. So, let's start with an inventory. What do we have in our solar system? Well, most of our solar system by mass is one star. 99, more than 99% of the mass of the solar system is in the sun. Orbiting the sun, there are 8 planets. And 5 official dwarf planets. There's actually more than that, but all the ones other than those 5 are. We're reasonably sure the dwarf planets, but we don't maybe have the best confirmation. But they've been declared dwarf planets in various papers and stuff, but not by the International Astronomical Union. There's only been 5 officially by the International Astronomical Union. More than 250 moons. That number's just out of date. I should probably update it. We keep finding more moons. Asteroids, interplanetary gas and dust, loads of Kuiper Belt objects. That's where most of the dwarf planets are, around the Kuiper Belt, and comets. And in the ancient times, we knew about a handful of this. We knew about the sun and the stars, 5 planets, 1 moon, meteors, and comets. So early astronomers knew about the moon, stars, Mercury, Venus, Mars, Jupiter, and Saturn, and also, excuse me, comets and meteors. Those are the things you can see without a telescope. Now the solar system is known to have 1 star, lots of moons, 8 planets. We added Uranus and Neptune, asteroids, comets, meteoroids, dwarf planets, and Kuiper Belt objects. And there's sort of a sketch. So in the center we have the sun, then we have the inner planets, Mercury, Venus, Earth, and Mars. Then we have the asteroid belt where most of the asteroids are, though not all. Then we have Jupiter, Saturn, Uranus, Neptune, and the Kuiper Belt. There's a number of dwarf planets in the Kuiper Belt. There's 1 dwarf planet in the asteroid belt. There may or may not be another planet out distant in the range of the Kuiper Belt. People are looking at the orbits of Kuiper Belt objects to see if they're maybe being disturbed by something, but nothing has been identified in any sort of surety. So every once in a while you'll see a story about a 9th planet. There might be another planet out even further. There also might not. We don't know. So here are some of the objects. We have Mercury, distance-wise, Mercury is at 0.39 AU. The Earth is at, Venus is at 0.72. The Earth is at 1. Mars is at, the moon is basically Earth. Mars is at 1.5. Ceres, that's the dwarf planet in the asteroid belt, is at 2.8. Jupiter is at 5.2 astronomical units. Saturn is at 9.5. Uranus is at 19.2, and Neptune is at 30. Things get much more spread out once you get past the asteroid belt. So consider that all the inner planets are within 1.5 astronomical units of the sun. The first of the outer planets, Jupiter, is nearly at 5. So it's more than 3 times as far away as from the sun is the furthest of the inner planets. There's suddenly a lot more room there. Pluto, 39.5, it's a Kuiper belt object. And then Comet Hale-Bopp has an average distance of 180 astronomical units. And then here are the masses. You can see most of these objects are smaller than the Earth. Venus is about the same size, it's about 80%. And then things like Jupiter, Saturn, Jupiter is much bigger than the Earth. Saturn is also bigger, and Uranus and Neptune are quite a bit bigger as well. And then the sun is enormous. Right? So we can know the distance from the sun for various objects by using Kepler's law, by studying how long they take to orbit the sun. We can figure out how far away they are from the sun. Because the orbital period can be observed. This lets us figure out, compared to the distance of the Earth from the sun. It turned out for a long time we knew how far every planet was from the sun in astronomical units, but we didn't know exactly how far the Earth was from the sun, because we hadn't figured out a good way to work it out. It's one of those funny things that can happen. We can figure out the radius of objects from looking at their size in the sky and knowing how far away they are. And then it's just some trigonometry. The masses can be figured out from Newton's laws, the way various things orbit them, or the way, basically. The rotation period can be observed. You can watch the object spinning. And density can be calculated if you know the radius and the mass. Because if you know the radius, you can figure out the volume. If you know the mass, then you can calculate the density. So all the orbits are pretty much exactly on the same plane, with Mercury being the most tilted. And then if you plotted Pluto on this, Pluto would be a lot more tilted. That's one of the things about Pluto's orbit that was weird. And here are some various objects. These are images of each of the planets and the sun. Don't think this might be to scale. Some might be a little small in this picture, and I think the inner planets are a little big. But here is a short video about the solar system. So Pluto's not a planet anymore. That's why it's not on that plot.
Our solar system is one of over 500 known solar systems in the entire Milky Way galaxy. The solar system came into being about 4.5 billion years ago when a cloud of interstellar gas and dust collapsed, resulting in a solar nebula, a swirling disk of material that collided to form the solar system. The solar system is located in the Milky Way's Orion star cluster. Only 15% of stars in the galaxy host planetary systems, and one of those stars is our own sun. Revolving around the sun are 8 planets. The planets are divided into 2 categories based on their composition: terrestrial and Jovian. Terrestrial planets, including Mercury, Venus, Earth, and Mars, are primarily made of rocky material. Their surfaces are solid, they don't have ring systems, they have very few or no moons, and they are relatively small. The smallest and closest to the sun is Mercury, which has the shortest orbit in the solar system at about 3 Earth months. Venus is the hottest planet, with temperatures of up to 867 degrees Fahrenheit due to an atmosphere of carbon dioxide and extensive lava flows. Next to this world of fire is a world of water, Earth. The water systems on this planet help create the only known environment in the universe capable of sustaining life. The last of the terrestrial planets, Mars, might have also supported life about 3.7 billion years ago, when the planet had a watery surface and moist atmosphere. Beyond the 4 terrestrial planets of the inner solar system lie the Jovian planets of the outer solar system. The Jovian planets include gas giants Jupiter and Saturn and ice giants Uranus and Neptune. The gas giants are predominantly made of helium and hydrogen, and the ice giants also contain rock, ice, and a liquid mixture of water, methane, and ammonia. All 4 Jovian planets have multiple moons, sport ring systems, have no solid surface, and are immense. The largest Jovian is also the largest planet in the solar system, Jupiter. Nearby is Saturn, the solar system's second largest planet. Its signature rings are wide enough to fit between Earth and the Moon, but are barely a kilometer thick. Past Saturn are the ice giants Uranus and Neptune. The slightly bigger of these ice giants, Uranus, is famous for rotating on its side. Next to Uranus is Neptune, the outermost planet in the solar system and also one of the coldest. Orbiting the terrestrial planets is the asteroid belt, a flat disk of rocky objects full of remnants from the solar system's formation, from microscopic dust particles to the largest known object, the dwarf planet Ceres. Another disk of space debris lies much further out and orbits the Jovian planets, the icy Kuiper belt. Apart from asteroids, the Kuiper belt is also home to dwarf planets such as Pluto and is the birthplace of many comets. Beyond the Kuiper belt is the Oort cloud, a vast spherical collection of icy debris. It is considered the edge of the solar system since that is where the gravitational and physical influences of the sun end. Our solar system's particular configuration of planets and other celestial objects, all revolving around a life-giving star, make it a special place to call home.
This is not the newest video. So there's been a lot of progress in our understanding of planets around other stars since that video was made. It said that only 15%. It's more like most stars actually we think have planets around them. But it's an active field of study. There's a lot of debate about exactly how common they are. We just keep finding them. As you know, as far as we can tell, the better we make our exoplanet detecting equipment, the more we find. We found literally thousands, like over 6,000 at this point. So the number of exoplanets is, and our methods for finding them are still pretty limited. So probably lots of them. So it's generally thought at this point that the planets are actually quite common. So the sun is like 99.8% of the mass of the solar system. So because the vast majority of the mass of the solar system is sitting in the sun, everything basically orbits around the sun. Because the center of mass of the solar system is essentially the sun. And then of the remaining matter, so this is a pie chart of mass of the solar system. It's kind of hard to read because it's basically all sun, as you can see. So if we look at not sun parts of the solar system, 90% of what's left is in Jupiter and Saturn. Jupiter is almost 3/4 of the mass of the the planets and everything else. So what remains for everything else is 0.02% of the mass of the solar system. It's a tiny speck of the mass. So here you can see this is Jupiter, this is Saturn, and this is Uranus, Neptune, and all the other planets. So let's talk about the planets. We'll start with the definition. A planet So this definition was finally put into place in 2006 by the International Astronomical Union, and this was the point where Pluto stopped being a planet. Basically, they found multiple other objects out in the Kuiper Belt. Particularly, they found one called Eris that was more massive than Pluto. And they needed to decide, okay, we're starting to find a bunch of these things that are like Pluto. They sometimes get called Plutoids. Are we going to add a whole bunch more planets? Or are we going to redefine what a planet is? Something similar actually happened with the asteroids. The asteroids were originally added as new planets, and then eventually they started to realize, oh, there's a ton of these suckers. We're actually just going to call them all asteroids and make them into bunch. And so what they did is they defined a new category. There is a planet, or a major planet is the way you can think of it. Then there is a dwarf planet, and then there's a minor planet, which is basically anything orbiting the sun. And a dwarf planet is sort of an intermediate thing, which is what Pluto is. So the definition of a planet orbits the sun, is massive enough to be pulled into a spherical and ellipsoidal shape, and dominates its orbit. It has cleared its orbit of debris. It needs to be by far the primary thing in its orbit by mass. So for example, the Earth, the mass of all the other stuff within Earth's orbit is maybe, I think it's maybe 1% of the mass of the Earth. I think it's less than 1% of the mass of the Earth. However, if you look at Pluto's orbit, the mass of everything else in Pluto's orbit is 20 times the mass of Pluto. That's sort of the differences we're dealing with. And it's mostly a technical definition, because we realized that there just had to be different categories. There wasn't a clear definition. So, yeah. So, there are 8 planets. They come in 2 categories. There are the terrestrial planets, which are close to the sun, Mercury, Venus, Earth, and Mars, and the Jovian planets, which are far from the sun. These are Jupiter, Saturn, Uranus, and Neptune. The terrestrial planets are close to the sun. They're close together. Their orbits are all spaced closely together. All of their orbits together are packed together in a space that's a fraction of the distance between any of the Jovian planets. They have relatively small masses and small radii. They're predominantly made of rock. They have solid surfaces and high densities. They rotate more slowly. They have relatively weak magnetic fields. They don't have rings, and they have few moons. There are 3 total for the 4 terrestrial planets. The Jovian planets are far from the sun. They have widely spaced orbits. They have large masses, large radii. They're predominantly gaseous. They don't have solid surfaces. They have gas that goes until the pressure gets high, turns to liquid. They have low densities. In fact, Saturn is less dense on average than water. They rotate more quickly. They have strong magnetic fields. They all have many rings. They all have multiple rings, and they have lots of moons. For the ones we know the least about, and I've counted the least moons, they both each have more than a dozen. So Uranus and Neptune have more than a dozen moons. Jupiter has like 90 something, and Saturn has more than 150, I think, at this point. We keep finding more. So, some of the differences between the terrestrial planets. The atmospheres and the surface conditions are very dissimilar on the terrestrial planets. So Earth has sort of medium atmosphere with nitrogen and oxygen in it. Venus has a very thick, dense atmosphere with carbon, made primarily of carbon dioxide. Mars has a thin atmosphere, very thin atmosphere made of carbon dioxide, and Mercury doesn't have an atmosphere. And that causes massive changes in surface conditions. Only Earth has oxygen in its atmosphere and liquid water on its surface, because the temperatures are Mercury and Venus are, well, Venus is too hot to have liquid water, Mars is too cold to have liquid water, Mercury is alternately too hot or too cold, depending on whether it's day or night. The side that's facing the sun on Mercury is incredibly hot. The side that's facing away from the sun on Mercury is incredibly cold. That's sort of how Mercury works out. Earth and Mars rotate at about the same rate. Earth is 24 hours. Mars is like 24.5 hours. Venus and Mercury are much slower. Mercury is every 55 days, and Venus is every 260, and it rotates backwards from all the other planets. Well, except maybe Uranus, but Uranus is on its side, so it's hard to say what's. Earth and Mars have moons. Mercury and Venus don't. Earth has one enormous moon. Mars has two dinky moons. And Earth and Mercury have magnetic fields, while Venus and Mars don't. So some smaller solar system objects. Moons. Moons are objects that orbit another object that orbits the sun. So they orbit a planet or some other larger object. So the Earth has the moon, Mars has Phobos and Deimos. There's an asteroid Ida, that has a moon called Dactyl. Here are the four biggest moons of Jupiter. Then there's a bunch more. Here are some of the moons of Saturn, like some of the bigger ones. Again, there's a bunch more. Similarly for Uranus and Neptune. These are some of the larger moons for each of them. There's more. They both have, I think, at least 14 moons. This is Pluto's large moon Charon. It has another 4 as well. Small moons. And then Eris, that dwarf planet that was discovered, has a moon called Dysnomia, and some of the other dwarf planets also have moons. So dwarf planets. Dwarf planets are things that orbit the sun that meet those first two categories of the definition of a planet. They orbit the sun. They're big enough to pull themselves spherical or ellipsoidal, but they don't meet the last category. They don't dominate their neighborhood. So that's like Pluto, Eris, Ceres in the asteroid belt. There's also Haumea and Makemake are the other official ones, but there's a bunch of other ones that people have observed and declared that they're dwarf planets, like Gong and others. But haven't been made official by the International Community, Astronomical Union. And then there are asteroids, meteoroids, comets, Kuiper Belt objects. These are various rocks that orbit the sun, for a loose definition of rock. Because far out in the outer solar system, a lot of what you're looking at there's a lot of ice, because it's cold. So the biggest difference between the asteroids in the asteroid belt and the stuff in the Kuiper Belt, asteroids in the asteroid belt are primarily made of rock. Objects in the Kuiper Belt are primarily made of ices, with rock in there, but they're mostly ices. Because out that far from the sun, it's cold enough that ices persist and act like rock. So a lot of the moons and the outer planets are covered in ice, and that ice acts like rock. There are volcanoes that spew water, that kind of thing. So here are some of the dwarf planets. This is Eris, Pluto, Makemake, Haumea, Ceres. Those are the 5 official ones. These were all discovered by 2006. And so stuff that's been discovered by that after that hasn't been made official just because they haven't had a meeting and they haven't bothered. There's a bunch of them out in the Kuiper Belt. Part of that was also because the way they did Makemake and Haumea was not as nice as the way they did Pluto and Eris. So there's some debate about the definition still. And then these are things like asteroids. These are some asteroids from the asteroid belt. So you guys are the Eros, Ida, Vesta, Ceres. And these are various things that orbit the sun. And there's like little tiny dust and little rocks and stuff all over the place as well. So here, this is a Kuiper Belt object. It's mostly like ice and snowy sort of structure. And these are the things that turn into comets when they get heated up by getting close to the sun. So this is the inner solar system. It shows the asteroid belt, some Earth crossing asteroids, and the Trojan asteroids. So the asteroid belt is where most of the asteroids are, but not all of them. And some asteroids have orbits that cross Earth's orbit. Those are called Earth crossing asteroids or near Earth objects. We have in fact discovered at least one asteroid whose orbit is entirely within the orbit of Venus. So they're not all out in the asteroid belt. And there's also two groups of them called the Trojan asteroids that are held stable by the gravity of Jupiter and the Sun in these two locations, in front of and behind Jupiter in its orbit. And I believe one of these groups also is called I cannot remember the other one. There's a version where one group is named after the Trojans, the other group is named after the Greeks from the other side of the Trojan War. The idea being that they're chasing each other. But I can never remember the other name because generally they're just both referred to as the Trojan asteroids. And they're sitting at what are called Lagrange points, which are like stable points in the gravity of two objects. So these are two of the Lagrange points. There's going to be a Lagrange point in between the objects. There's one beyond it. There's like 6 total for any orbit. Here is the path of Icarus, which is an Earth-crossing asteroid. It's important to track these because they could potentially interact with the Earth. Unfortunately, because they can get close to the Earth and get disturbed by the Earth's gravity, they're much harder to predict because when they get disturbed by Earth's gravity, their orbit changes. So that's sort of an issue. And what that means is that little differences in our knowledge of the orbit can lead to big differences in where it ends up. Here are some asteroids and meteoroids, which are made of, asteroids and meteoroids are rocky. The difference is asteroids are bigger. So this is asteroid Matilda. This is asteroid Ida with its moon Dactyl. This is asteroid Itokawa. And the dinosaurs were probably killed by the after effects of the impact of a large meteor or a small asteroid. We know that impact happened. There's some debate about whether it was the complete cause of the extinction or not, but general agreement is that that's what caused the extinction. And it would have been disastrous anyways. But we know what happened because we found a crater. The crater is off the Yucatan Peninsula in Mexico. It's the Chinook crater. And it's still there. I mean, it's hard to see because 65 million years of erosion have happened, but there is evidence of it. And there's a layer of basically debris from the asteroid covering the entire Earth. Like if you dig down, there's this line that's got more indium in it that came from the asteroid impact. And the larger the impact is, the less often we expect it to occur. And actually over time, the probability of impacts goes down because basically the solar system is running out of big rocks that can run into things. So smaller events on the scale of maybe 5 kilotons, they happen all the time. But they tend to blow up in the upper atmosphere. Larger events, maybe 1,000 years, are things like the Tunguska event, which blew up. That actually blew up in the atmosphere, but it blew up close enough to the ground that it flattened a bunch of forest and was observed over huge distances. It occurred in, luckily it occurred basically in the middle of nowhere in Siberia, but, well, no, I don't know if it's Siberia, but in the middle of a forest. And then you get into the really big things. The extinction of the dinosaurs is the kind of thing that happens every 100 million years or so. So that's sort of the scale. Here's the asteroid Eros. So you can see it's ball of rock, it's sort of lumpy, it's got a bunch of impact craters on it. Some asteroids are really not very good. Some asteroids are more consolidated. Some of them are basically piles of gravel held together by gravity. So there was actually an issue with one of the missions that was sent to sample from an asteroid, where the asteroid was much less densely packed. It was much looser than we thought it was going to be. Caused some issues because it threw up a bunch of debris when the sample mission was leaving, and it sort of stuff got stuck in places. But it came back successfully, and we were able to sample. Comets are primarily made of ice, ices, and they have some rocky parts. So it's like a ball, a dirty snowball is often how they get described. If they have an orbit that gets close to the sun, they get some interesting things where they get a hard outer layer made of, because when they get close to the sun, they heat up and the ice is vaporized. But they can cook off like organic material and such, and basically have a burnt on crust. And then the material comes out of that through cracks in that burnt on crust. And what you see is the cloud of gas that's escaping around it. That's the coma. And then there's a tail of material being blown off by the sun. So that material is either dust being pushed away by sunlight or gas being pushed away by the solar wind, because the sun spews out charged particles all the time. So the solar wind means the ion tail from a comet will always point directly away from the sun. But the dust tail also tends to point away from the sun, but the dust particles are more massive and move more slowly. So they're affected more by the movement of the comet, so you get a slightly curved tail. And you'll notice that the tails here always point away from the sun. They don't trail behind the comet. So every time you see a comet drawn or animated where the tail is trailing behind it, that's wrong. And in fact, for a portion of the trip, the tail is pointing in the direction the sun is going, because that is away from the sun. So these jets of stuff, so there's sort of a harder crust and jets of material of gas and dust come out of the comet's nucleus. This is the dense central part, as it's warmed up by the sun. And that's what forms that coma, the glowing sphere around it, and then the tail behind it. Now, there's sort of two groups of stuff that can become comets. The stuff we see as comets that are dramatic are these icy objects that have very elliptical orbits and manage to get close enough to the sun to heat up enough to have that tail and coma. So those are things that get close. But the size, shape, and orientation of the orbits of comets depend on where they are. So the Oort cloud comets have really irregular orbits that are randomly distributed, and they rarely ever come anywhere near the inner solar system. The Kuiper belt has a bunch of stuff that sits in stable orbits in the Kuiper belt, but there are some objects that do have more irregular orbits, more elliptical orbits that actually come close to the sun. And the bigger a comet's orbit, the longer it takes to return. So some of those Kuiper belt objects can take centuries for each orbit. Longer than centuries, really long times. And it turns out meteor showers. So there's these annual meteor showers. Meteor showers are actually associated with comets. So as comets break up, they leave behind debris in their orbit. And that debris is just sort of traveling along in their orbit, and there's sort of a steady supply of debris along the orbit. And if that orbit crosses Earth's orbit, well, that material is just gonna be there, and Earth is gonna pass through that dust. And when Earth is passing through a bunch of dust, that dust burns up in the atmosphere, and you get meteor showers. And that's why the meteor showers happen at the same time every year, because there's this effectively trail of dust that the Earth flies through every year. And there's also stuff in between the planets. There's interplanetary matter. So this is sort of gas and dust between the planets and how it's distributed. And this is all in the infrared. So, and when a large meteor hits the ground, it can create a significant crater. One of the most dramatic meteor craters on Earth is the Barringer meteor crater in Arizona. This is about 1.3 kilometers across. 170 meters deep. And this is a relatively young crater. It's only 50,000 years old. So it killed everything around it when it impacted. I believe there is some evidence of that mass kill off of it, megafauna around it. But it didn't kill any humans, because humans hadn't made it to North America by that point. But yeah, this was a very dramatic crater. It's very well preserved because it's in the middle of a desert in Arizona. So it's dry, it doesn't get eroded much. This is the Manicouagan Reservoir in Quebec. This is a larger impact crater. It's an older one. It's not as nicely preserved, but you can see the crater here. So, just an idea of the scale. Most of the solar system is empty. If the sun were a ball, about 25 centimeters, about 10 inches in diameter, Mercury would be less than a millimeter in size, and it'd be 10 meters away. Earth would be a little over a millimeter in size and over 27 millimeters away. Jupiter would be about 2.5 centimeters, an inch across, and over 140 meters away. Pluto would be less than 0.5 millimeter in diameter and over 1 kilometer away. And Alpha Centauri, the nearest star, which is about the same size as the sun, would be about the same size and nearly 7,500 kilometers away. That's almost 1/4 of the way around the Earth. Well, no, it's more like 1/6, but it's a significant portion of the circumference of the Earth. So, how are various objects in the solar system named? There's a bunch of formal conventions for it. Just so everyone agrees, they put together some rules. So, planets and moons are named after gods and heroes, usually from Greek or Roman mythology. The exception is Uranus. That is the moons of Uranus, are named after fairies from Shakespeare. Uranus is named after a Greek. Well, it's named after a god from Greek or Roman literature. It did actually break the rules on its naming convention there, because they used the Greek name instead of the Roman name, and then they Latinized it, which is why it's sort of very weird in its name. Comets are named after their discoverer. If you discover a comet, it's named after you. If you're the kind of person who discovers a lot of comets, they get numbered. So in the 90s, there was a comet that impacted Jupiter. It was really dramatic to see because you got to see a comet slamming into Jupiter. It also gave you an idea of the scale. It was kind of small compared to Jupiter. And that was Shoemaker-Levy 9. Because Shoemaker and Levy had discovered 9 comets, I think the 9th one. Asteroids are named by the discoverer. You can name them, if you discover an asteroid, you can name them however you want. So that I believe the similar thing is true for Kuiper Belt objects, but a lot of these are actually got awful names that are just like some letters and some numbers because they're just code names from a survey of how they were found. They haven't been given pretty names yet. And then there are the features on various objects. They have individual naming conventions. Like there's rules for how you name, who and how you can name features after, kind of thing. For each object. And because there's so many of them, and so it's like categories of people, or like craters are named after famous scientists on the moon are named after famous scientists. Certain types of features on Pluto and Charon were named after death gods of various sorts. Or and then there was another thing like, but other ones where you were allowed to name them after fictional science fiction characters. Like each sort of, there's just so many things that need names. So our solar system contains a wide variety of types of objects, but the sun is most of the mass, and smaller solar system objects have varied structures and features. And a scale model of the solar system is nearly impossible to construct because of the immense distance between planets. And there's actually been a few controversies about the naming stuff. Usually what they've done is that it turns out the person they named some feature after is a terrible person. And so they may generally try and rename it after another person who has the same last name. So they don't actually have to change anything. But they're no longer supporting the charitable person. That happens quite a bit. Well, that's happened a few times. There's a lot of things that need names. And there's some work to try and name them over a larger variety of people. Spreading it out, not just Western famous people in the West. Trying to recognize people from other countries who did other things, not just naming everything after Western science. Especially because we used up a lot of them already. But yeah, a lot of stuff, a lot of random space racks or random space things just have names like SJ205 or something. Because it's the 205th object discovered in this survey or something like that. When you're doing this big surveys where they're like automated and they just find all the stuff, you can. A lot of them just get numbers. And then later, if they're interesting, they'll get names. So the types of planets, there's two types. There's the terrestrial planets, they're similar to Earth. Mercury, Venus, Earth, and Mars. Venus and Earth are the most similar of these two. They're similar in size, similar in gravity. Mercury is smaller. Mars is also smaller. The Jovian planets, they're called Jovian because they're Jupiter-like. Jupiter is the biggest of these. Jupiter and Saturn are very similar. The Saturn is sort of a smaller version of Jupiter, and Uranus and Neptune are very similar. So the properties, the terrestrial planets are small in size and mass, they're rocky, they have a solid surface, they have a high density, they rotate slowly, they have weak magnetic fields, they don't have rings, and they have few moons, and they're close to the sun. The Jovian planets are large, they have a thick gaseous atmosphere, they're primarily negative gas, they don't have solid surfaces, just eventually the gas turns into a liquid from the pressure. They have a low density, they have fast rotation, they have strong magnetic fields, they have rings and many moons, and they're far from the sun. And why we ended up with these two categories has to do with how the solar system. So why are there two types of planets? They were formed at different temperatures. The inner solar system is hot, relatively speaking, especially in the early solar system, it was hot. What that meant was, when you're close to the sun, the only stuff that could condense to form planets was rock and metal, stuff that has very high melting points and vaporization points in this context, but yeah. And this gave us the terrestrial planets. While far from the sun, things like ices could condense and form, giving us a lot more material and allowing larger planets to form. This allowed a larger core, and once you got above a critical size, you could start collecting the most common material in the early solar system, hydrogen and helium. And then you get real big. So it's sort of, once you get big enough, you start snowballing. Because bigger things have more gravity, so they can collect more, so they get bigger, and that process continues. But the inner planets were just too small. So helium, for example, all the helium on Earth is formed from radioactive decay underground. Because if you release helium into the atmosphere, it will literally, it's so light, it will literally just leave. It'll float up and eventually leave the atmosphere. Earth's gravity isn't strong enough to hold on to it at the temperature of Earth. So all the helium we have has been formed. So helium is the second most common element in the universe. It's relatively rare and expensive on Earth because of this. So planets also change over time. So one of the things, if you get a ball of stuff hot enough and liquidy enough, basically, the heavy stuff will sink to the center. And that process is called differentiation. It's the separation of materials by density. So the Earth, for example, has a metallic core, a rocky mantle and crust, and a gaseous atmosphere. The densest materials in the center, and you get less dense as you go up. You can also have geological activity. If your interior is hot enough, that can drive motion at your surface. That's happening on Earth. Earth is one of the more geologically active objects in the solar system. And another major factor for planets is impacts. That's one of the main ways that surfaces get changed. So for example, on the moon, the main way the surface of the moon gets changed is by being hit by space rocks. And that is in fact the only form of erosion on the moon. So things on the moon stick around until they're hit by space rocks. So impact reduces surface. So geological activity, you can get volcanoes, all kinds of activity like that. And then lastly, impacts can change the surface. And most largish roundish objects in the solar system have differentiated. There are a few exceptions on that. But like, you know, for example, most of the big moons of Jupiter have differentiated. So there are also swarms of small objects. There's lots of rocky asteroids and icy comets that populate the solar system. You know, there's lots of little rocks flying around the sun. So there's two distinct types of planets. They formed in different regions of the solar system because of different temperatures that existed there. And the solar system surfaces have been modified over time via various processes. You know, some places have lots of geological activity, so surfaces don't last very long, like Jupiter's moon Io. Some places have surfaces have been the same, except for asteroid impact, you know, meteorite impacts for billions of years. So you can find, you know, for example, on Earth, Barringer Meteor Crater, one of the best preserved craters on Earth, it's only 50,000 years old. You can see similar looking craters on the moon that are 3 billion years old. You know, that are billions of years old. So, how do we figure out how old something is in the for an object in the solar system? So, how do we measure the age of various objects? Well, one way is that it turns out the amount of stuff whacking into other stuff is more or less the same everywhere in the solar system. So you can count craters. More craters mean an older surface. Now, the rate of impacts has slowed down over time. Because if the rate of impacts was the same as it is now, like the surface of the moon would be significantly older than we know the solar system is. But we can count craters, and any surface that's been hit by more stuff over time, that's an older surface. That lets us compare the ages of surfaces. But if we want to figure out the exact age, we have to make a bunch of estimations to get a number out of that kind of stuff. If we want to figure out the exact age, we can use radioactive materials in rocks. Because when certain types of rock form, there are radioactive materials in their structure, and those radioactive materials decay over time, slowly. And so by studying how much of the starting material and how much of the product are in that rock, you could figure out how long it's been decaying, and figure out its age. So this is also how we date rocks on Earth. And this process, amusingly, a side effect of this process, because of this sort of decay, is how we figured out that leaded fuel was just truly awful. People were collecting lead samples for use in dating, because lead is a product of one of these radioactive decay chains. And they discovered this massive spike in lead in the environment, starting from other methods of figuring out how old things are, from when the leaded gasoline started being used. So, how do we determine the relative age of things? We count the craters. So, cratering rates have been the same throughout the solar system for billions of years. They've been, you know, roughly the same rate here near Earth as there is out near Jupiter or Neptune or wherever. So the more craters on a surface, the longer it's been exposed. So, and this tells you sort of how active the surface is, because geological and weathering effects will slowly wipe out evidence of craters. So for example, the Earth has very few craters, while the moon has lots. So the Earth's surface is younger, and having been reworked by various geological and weathering processes. And we know this from other ways of dating the Earth's surface. Most of the Earth's surface is relatively young. So on the moon, there are two main types of regions. There are the Maria, which are these dark areas. They have few craters. It's a younger surface. And then there are the highlands, the light regions. They have more craters. It's a higher surface, an older surface. And this has actually been backed up by dating the rocks of these surfaces. Our understanding of the Mare is that they were caused by very large impacts that cracked the moon's crust, and those craters flooded with lava. So these are basically massive lava floods of basalt, and that's why they're smooth and dark, because they happened more recently. But if we want to figure out exactly how old something is, well, we need to get a rock from that surface. We need to bring something back. So we're actually pretty limited in the number of actual objects we have an absolute date on. Because it's hard to bring samples back to most places in the solar system. We've done it for the moon, we've done it for a handful of asteroids. We're working on doing it for Mars. But yeah, you need a sample. All rocks have some radioactive materials in them that decay over time. And some of these are not very radioactive at all. Like the useful ones are often not super radioactive because you want them to decay over a long period of time. Because the amount of time, the rate at which they decay, it determines the amount of time over which you could use them as a dating tool. So if you want to measure long periods of time, which is what you often want to do with these rocks, you want to use slower decaying materials. Faster decaying materials are good for younger things. You may have heard of carbon dating. That uses carbon-14, which as these materials go is a relatively quick one, but it is replenished by our interactions with the atmosphere. So things while they're alive get carbon-14 by breathing. Well, exchanging with the atmosphere, let's put it at that. But you breathe, you eat plants that get carbon from the atmosphere, and the carbon-14 in the atmosphere is continually replenished because it's generated at the top of the atmosphere by cosmic radiation and the solar wind. And then we can use that to determine how long it has been since that thing died, because it stops getting carbon-14 once it dies. Similar thing with rocks. When rocks form, they have certain elements in them that are radioactive, and those decay over time. But often, carbon-14 has a half-life in the thousands of years, or some of the rocks we use for dating rock, some of the things we use for dating rocks have half-lives on the order of billions of years. Much larger scale. The half-life is the amount of time required for half the original parent atoms to decay into new daughter atoms, and comparing the ratio of parent to daughter atoms can give us the age. Sometimes it's a little more complicated than that, because sometimes what will happen is it'll decay into one thing and then that thing will decay into another thing, but that's the general idea. So potassium-40 has a half-life of 1.3 billion years. Potassium-40 is also why bananas are radioactive. Ever so slightly. Not a big deal amount of radioactivity, but yes. So every 1.3 billion years, half the potassium-40 will decay into argon-40. So if in a sample, only 25% of the potassium-40 remains and 75% is changed to argon-40, 2 half-lives have passed. That's sort of the way this works. So this means the sample is 2.6 billion years old. If you only have an eighth of the potassium-40 left, 3 half-lives have passed. This means the sample is 3.9 billion years old. So this is good for dating really old, rocks on the scale of the age of the solar system. So we can measure the ages of objects in the solar system. Relative ages can be determined by crater counts, and absolute ages can be determined by radioactive decay. And we use different elements for different time scales, basically. Because if you were trying to figure out how old something was that was only, tens of thousands of years old, like 50,000 years old or something, potassium-40 wouldn't be very useful at all because it would have barely decayed. You need to use something that decays faster so you can actually see how it changed. But if you have something that decays faster, it'll be all gone in the billion years that you'd have to use potassium-40 for. That make sense? So let's start to talk about our understanding of how the solar system formed. So we can learn a lot about the origin of the solar system by looking at the patterns that remain today in the solar system. So some of these patterns, all the planets orbit in approximately the same plane. Most of the stuff in the solar system is all in one flat disk. It's flat. All the planets orbit around the sun in the same direction. Most of the planets rotate around their axes in that same direction. So, the planets are going around the sun and they're spinning in the same direction that they're going around the sun. There's a couple of exceptions. That is Venus and Uranus. Uranus is on its side, Venus is going backwards, but real slow. The planets are separated by type into two types, terrestrial and Jovian. And there's a bunch of little leftover bits, asteroids, comets, and small bodies throughout the solar system. So here are some of the clues. The large bodies all rotate around the sun in the same direction. Most bodies sort of revolve around the sun in the same direction. Most bodies rotate in the same direction. And there's terrestrial and Jovian planets, and there's a couple of exceptions on the rotation stuff. So
This cosmic context figure from your textbook summarizes 4 major features of our solar system that must be explained by any theory that seeks to describe how our solar system formed. The first major feature is that the large bodies of our solar system have orderly motions. This oblique view shows that the planets all orbit the sun in the same direction, counterclockwise as viewed from high above Earth's North Pole, and in nearly the same plane. Switching to a top-down view, we also see that although planet orbits are elliptical in accord with Kepler's first law, these ellipses are very close to being circular. Moreover, the small white arrows indicate that, with the notable exceptions of Venus and Uranus, most planets rotate in the same counterclockwise direction that they orbit the sun, and the red circles show that major moons generally orbit in their planet's equatorial plane and in the same direction that their planet rotates. Before we continue, think back on what you've learned about the laws of nature to answer this question. Notice that the sun also rotates in the same counterclockwise direction that the planets orbit. What law of nature explains why the sun should have been rotating after it formed from a collapsing cloud of gas? Is it the law of conservation of angular momentum, the law of conservation of energy, the universal law of gravitation, or Kepler's first law of planetary motion? The answer is A, the law of conservation of angular momentum. This is because a collapsing cloud almost inevitably will have some small net rotation, so as it contracts in radius, its rate of rotation must speed up. In fact, the sun probably once rotated much faster, but has transferred angular momentum over time to the planets and to interplanetary gas. Moving on, the second major feature is that the planets fall into 2 major categories, which we call terrestrial, which means Earth-like, and Jovian, which means Jupiter-like. In our solar system, the terrestrial planets are the 4 inner planets, Mercury, Venus, Earth, and Mars, and we generally count our moon as a 5th terrestrial world. The Jovian planets are the 4 outer planets, Jupiter, Saturn, Uranus, and Neptune. They are actually much larger in comparison to the terrestrial planets than shown here. Comparing the categories more generally, the terrestrial planets are small in mass and size, relatively close to the Sun, made mostly of metal and rock, and have few moons and no rings. In contrast, Jovian planets are much larger in mass and size, orbit far from the Sun, at least in our solar system, are made largely of hydrogen, helium, and hydrogen compounds such as water, methane, and ammonia, and those in our solar system all have rings and numerous moons. The third major feature is that in addition to the planets, vast numbers of small bodies also orbit the Sun, represented here as swarms of individual dots. We generally call these asteroids when they are rocky in composition, and comets when they are ice-rich. Some of these small bodies are large enough that we call them dwarf planets, as is the case with Pluto, Eris, the asteroid Ceres, and a few others. Most asteroids and comets are found in three major regions of the solar system. Asteroids are concentrated in the asteroid belt between the orbits of Mars and Jupiter. Most comets are found either in the Kuiper belt that lies beyond the orbit of Neptune, or in the far more distant region we call the Oort cloud, which is roughly spherical in shape because its comets have orbits that are randomly inclined to the ecliptic plane. Our fourth major feature is that there are a few notable exceptions to the general rules described in the first three features. For example, while most planets rotate in the same direction as they orbit, Uranus rotates nearly on its side, and Venus rotates backward compared to its orbit. Another important exception concerns our own moon, which is the only large moon found around a terrestrial planet in our solar system. As you will learn soon, the quest to explain these four features led scientists to our modern nebular theory of solar system formation, a theory that not only explains the origin of our own solar system, but also explains the many other planetary systems now known to exist.
So those are some of the possible features. So all large bodies in the solar system, let me just check where I'm at. Oh, okay. Orbit in the same direction and in nearly the same plane. Most of them also rotate in that direction. Terrestrial planets are rocky, relatively small, and close to the sun. The Jovian planets are gaseous, larger, and further from the sun. And there are several notable exceptions to the normal patterns that do need to be explained. So the model needs to be able to explain the exceptions. Uranus is weirdly tilted, Venus rotates backwards and slow, and Earth has a relatively large moon. So again, we can look at these patterns that were mentioned, and we can try and create a model of the creation of the solar system that explains these patterns. So if we think the nebular theory is that the solar system started as a nebula, cloud of gas and dust, which collapsed to form the solar system and all the stuff in it. So according to the nebular theory, our solar system formed from a giant cloud of interstellar gas, a nebula, which something happened that caused it to start collapsing under its own gravity. And as it did, it spun up faster and faster and condensed. Most of the material went to the center and condensed into the sun, but some material spun out into a flat disk, and that disk condensed to form the planets and the other stuff in the solar system. And the origin of this nebula, it's like the nebula we found, it's leftovers from previous stars. So elements that formed the planets were made in stars and then recycled through interstellar space. So much of the elements that make you up had to have been formed in a star. With one notable exception, that's hydrogen. The hydrogen that makes you up was probably actually formed in the Big Bang. And a significant portion of you is hydrogen. You can take a lot of hydrogen. But most of the elements that make you up were formed in stars. And the sort of stuff that makes dense planets all need stars. Anything heavier than helium, or I guess a tiny bit of lithium, but I mean, basically anything heavier than helium had to be formed via the process of a star creating it and generally dying. So the solar system formed from a large cloud of gas and dust, primarily hydrogen gas that started collapsing around 5 billion years ago. The rotation of that cloud is reflected in the motion of the planets today. Cloud was rotating a little bit in the direction that all the planets are revolving around the sun, but because it collapsed and got a lot smaller, everything had to spin a lot faster. Like when you pull your arms in when you're spinning, you spin faster. Just on a much larger scale. The hotter temperatures near the sun would cause different types of materials to condense. Heavier rocky materials and metals were the only ones that could condense near the sun, while further out, hydrogen compounds, ices, could form into larger structures. And the small bodies are leftover remnants of planetary formation. And most of the exceptions can be tied to large collisions. So we had a cloud of gas and dust that contracted due to gravity, and the conservation of angular momentum meant it spun faster and faster as it contracted. And condensation theory says that condensation occurs when the gas cools and changes its state to become small solid particles. And these interstellar dust grains attracted more material, acted as nuclei for condensation. And then they started colliding with each other and sticking together, forming planetesimals and then eventually planets. And so conservation of angular momentum says that the product of radius and rotation rate needs to be constant. So if you have a large radius and a slow rotation rate, if you condense to a small radius, you end up with a high rotation. So as a dust cloud collapses, its rate of rotation will increase. And we see this with lots of stuff. When things collapse, they end up spinning faster. So when the cores, some of the fastest spinning things out in the universe are things where it was the core of a star that collapsed and became very small and ends up spinning very fast. So this is what's known as the nebular hypothesis. But I don't think we have time for this today. So we'll get back to this next time. So that's most of chapter 7. I'll see you all next week. Remember that the test will be next week on Thursday, and you do get one sheet of notes. So we'll finish chapter 7 on Tuesday next week. And we should be able to start the next chapter as well. So get a little ahead. And then your test will be on Thursday next week. Thursday, the 11th. That's also when all the homeworks are due. And stop sharing. Okay. I'm going to end the meeting for all.